Great. Okay. I hope you can all hear me okay. So thanks very much for joining today. I'm obviously very, very sorry that we can't meet in person, even for this rearranged meeting 1 year on. But hopefully things will get back to more normal soon. Okay, so it's a great privilege to tell you about some of the observational constraints on our theory of cosmic inflation. And in this talk, I want to review both the current status and look forward a little bit to the future and think about future prospects. So, observations in cosmology over many decades now have led us to a picture where we think that the early universe was actually incredibly simple. So in terms of the sort of fluctuations in the early universe, we believe that all the structure we see now essentially evolved passively from early times. So it started off very, very simple and then just evolved under gravity and the other laws of physics. And of course, that can actually lead to a very complex late time universe because of nonlinear evolution. But at least at early times, we think the fluctuations were very simple. So they evolved passively. They were initially Gaussian, adiabatic, and had a nearly scale invariant primordial spectrum. We have no evidence yet for primordial fluctuations in anything other than the scalar mode. So we only have curvature fluctuations as far as we know. And we have this very peculiar property that there are sort of apparently acausal, so super Hubble correlations, which are difficult to explain in the standard Friedmann-Robson-Walker cosmology. In terms of the particle content of the universe, well, we have essentially the standard model particles plus dark matter. And dark matter, okay, we don't know what it is, but we know phenomenologically that it has negligible velocity dispersion and essentially no interactions with the standard model. And we have no evidence for example, non-minimal mass neutrinos. There's no evidence for additional light species, and those neutrinos that we know have to be present in the standard model, their masses are consistent with the minimum masses that are allowed by oscillation experiments. And then in terms of the late time universe, of course, that's, as I said, much more complicated because we're seeing a highly non-linearly evolved universe. But it seems to be consistent with this very simple picture where the dynamics of the universe is now dominated by a cosmological constant, causing the universe to accelerate in its expansion. So an obvious question, where did this very simple initial conditions for the universe come from? And of course, we don't know, but for many, would say that our best for what went on in the early universe was this idea of cosmic inflation. So you all know a lot about this. I don't really need to introduce it. It's the theme of this workshop and these lecture series. But just to remind you that the key idea is that you have quasi-exponential expansion, and that means that the co-moving Hubble radius, so that's 1 over the scale factor times the physical Hubble radius, that decreases exponentially during this inflationary phase. So if you start with a fluctuation on small scales initially, so a small co-moving scale that's well inside the Hubble radius, as inflation proceeds, the co-moving Hubble radius will shrink and quantum fluctuations in that small scale mode will appear essentially as classical curvature fluctuations on super Hubble scales once inflation proceeds and that mode exits the Hubble radius. And then at some later time in the evolution of the universe, the universe reheats, inflation ends, and then we have the standard hot Big Bang evolution, in which case the co-moving Hubble radius is then growing again, and this mode comes back inside the Hubble radius at some later time. And of course, we observe the fluctuations way over on the right of this plot today. This theory is, or at least the general paradigm is very, very testable. It makes a number of key predictions, many of which we've verified. The exponential expansion naturally leads to the prediction of a spatially flat universe, and we've verified flatness at the sort of 0.2% level now. You would expect any pre-inflationary defects to be significantly diluted, very significantly diluted by inflation, and that's consistent with what we observe. We see a power law spectrum of primordial fluctuations, again consistent with expectations, and it's close to scale invariant, but not exactly scale invariant. The fluctuations appear to be Gaussian, as far as we can tell, and they're adiabatic. So in the early universe, there were no relative perturbations in the number densities of different species. So that's all well and good. The one sort of missing ingredient is that in many models of inflation, particularly those that occurred at a high enough energy scale, you would expect to see a detectable background of primordial gravitational waves or tensor perturbations. And these have not yet been detected. And that obviously puts constraints on how energetic or essentially how fast the universe was expanding during the inflationary phase. And our current limits are that this tensor to scalar ratio, given the ratio of tensor power to scalar power, is less than about 0.06. Okay, so the rest of this talk, I'm really going to review, where those constraints come from, what data goes into getting those constraints, what's the actual physics underlying the observable process of testing inflation in this way. And then I'm going to move on to look at sort of future prospects. Is there a question, sorry, from Arthur?
Yes, if I may, you presented these numbers, I mean, as confidently as we all heard them over many years. But now with the H0 problem, I heard that many things are at stake and could be kind of very different. For example, that the scale spectrum could be perfectly scale invariant if you resolve the H0 problem in the right way. And that worries me, that now maybe everything has to be rethought. I mean, how worried are you about still showing these numbers and the error bars in the face of the H0 problem?
Yeah, so I'm not really going to say very much in this talk about issues with H0. I mean, what I would say is that, yes, there clearly is, I don't think it's even appropriate probably to call it a tension now. There's a very significant 4 or 5 sigma statistical difference between direct measurements of H0 and what we infer from basically extrapolating the early universe forward in time. You're right, some of these numbers, of course, do change. So, for example, one way you can try and resolve the H0 problem is by having some additional light relativistic species. That can allow you to have a larger H0 consistent with direct measurements. The effect of that is that if you increase the number of relativistic species, you tend to reduce the power observed in the microwave background on small scales. You can compensate that by making the scalar power spectrum somewhat bluer, taking you more towards scale invariance. I mean, that's true. You can play that sort of game, but that model, for example, does not actually provide a very good fit to the microwave background data. It really doesn't want those additional relativistic species, and we'll be able to test that actually exquisitely with forthcoming polarization data. So I think, yes, we should absolutely be mindful that these numbers, may well be subject to some modification. But the problem is, of course, we don't know how to resolve the Hubble tension, let's call it, at the moment. So without a concrete model, it's very difficult to say, quantitatively how these numbers will change. And I think it's fair to say that they're, the sort of models that do seem to provide some hope of resolving the Hubble tension. You're right; they do involve changes in the relatively early universe. So you might, for example, change the expansion rate around the time of recombination, and the consequence of that is that there might be some changes in some of these numbers. But I think the basic picture is not going to change. At least that's my opinion. So sure, the detailed numbers might change.
Thank you.
Okay, so I mean, the sort of key observable we use to test inflation, you know, the primary thing so far we've used is the fluctuations in the microwave background. So this is just a picture of the temperature anisotropies from the Planck satellite. And the reason the CMB is so powerful is because, you know, it's our earliest probe of what conditions were like in the early universe. So in particular, we're seeing a relatively unprocessed version of the primordial fluctuations. The processing just involves sort of linear physics, which is very well understood. So, you know, we can very accurately produce statistical predictions given a model for what the fluctuations ought to look like in maps like this. So given a lot of this talk is going to be about the microwave background, let me just spend a couple of minutes just with a quick primer about the physics of the microwave background. So we normally talk in terms of power spectra. So we make a spherical harmonic decomposition of say the temperature field on the sphere, or equivalently, you can think of this as just sort of doing a Fourier decomposition. And then we plot the angular power, which is essentially the variance of the fluctuations as a function of scale, where large scales are on the left in this plot and small scales are on the right. So if you do this, the temperature power spectrum looks like the black line at the top here. And on large scales, you're effectively seeing a very unprocessed form of the primordial perturbations. Whereas, so you know, you're essentially seeing the slight tilt in the primordial spectrum on these scales. And then on smaller scales, you're seeing the effects of gravity, acoustic physics, and photon diffusion processing those primordial fluctuations in a linear way. And in particular, you get this series of acoustic peaks that allows you to measure very precisely, for example, the particle content of the universe. The microwave background is also linearly polarized, and that just arises from around the time of recombination when the CMB last scattered. If the radiation was anisotropic, the scattering will produce partial linear polarization. And we can decompose the polarization field on the sky into two geometric modes, one called the E mode, shown here in blue, and then another mode called the B mode, which I'll discuss in a second. So the E mode is kind of rather similar in origin to the temperature fluctuations, in the sense that if you have primordial curvature perturbations, they will source the temperature fluctuations, and they'll also source the E mode polarization. The spectrum is significantly different in polarization because you're primarily probing velocities at the time of recombination rather than what the density in the photons are doing. But you still see the same structure of acoustic peaks, for example, albeit with a different phase. There's an interesting signal on large angular scales in the E mode polarization due to rescattering around the time of reionization, when the first stars formed and reionized the universe. And that can give us interesting constraints on, for example, the astrophysics of reionization. And then finally, the B mode of polarization. So this is a kind of curly pattern shown by this little figure here. And the reason this is a very important mode of polarization is that in linear theory, curvature fluctuations cannot produce by symmetry B mode polarization. So, you know, if we observe primordial B modes, then we're seeing something other than scalar fluctuations. So most plausibly, we're seeing the effect of primordial gravitational waves or tensor modes. And I've just shown here the B mode power you would expect for a tensor to scalar ratio of about 0.07, which is about the upper limit from CMB experiments. So what you can see is, you know, it's a really tiny signal. It's much smaller, many orders of magnitude smaller than the temperature, and significantly smaller than the E mode polarization as well. You'll also notice that there's a dashed line here, which is another B mode signal. And this is due to gravitational lensing. So this is a sort of second order effect, whereby as the microwave background propagates from the time of last scattering, it's deflected by all the large scale structure in the universe. And this can actually transform some of the E mode into B mode polarization. And this turns out to be a very important background that you want to try and get rid of if you're trying to measure this primordial signal. Okay, the other probe the cosmological observable that's very important are probes of large-scale structure. So this is just an example of the galaxy distribution from the Sloan Digital Sky Survey. And with surveys like this, there are many observables that you can actually extract. You can look at the clustering of galaxies. You can look at how their shapes are affected by large-scale structure, so that's weak gravitational lensing. You can look at what's called a Lyman alpha forest. So this is probing neutral hydrogen in the intergalactic medium and looking at the absorption in the Lyman alpha transition of the spectrum of distant quasars as it passes through the intergalactic medium. You can identify galaxy clusters and look at the abundance of them as a function of mass and redshift. You can look for what's called 21 centimeter absorption. So this is absorption of the microwave background itself by the 21 centimeter absorption, the 21 centimeter transition in neutral hydrogen. And you can also do what's called line intensity mapping. So instead of trying to resolve individual galaxies, you can sort of look for the integrated effect of large-scale structure, so clustering in the unresolved sort of diffuse background radiation emitted by galaxies. And all of these properties are extremely important for constraining cosmology in different ways. And I'll touch on several of these throughout the talk. Okay, so let me just quickly just run through what the basic techniques are for testing some of these inflationary ideas before we look at some of the current constraints. So spatial curvature, as we know, inflation predicts something very, very close to a flat universe. And the way we can test spatial curvature is essentially by taking some standard ruler and measuring its angular size at different redshifts. And we're very fortunate that the microwave background provides a very nice such ruler, which is the sound horizon at the time of recombination. So the distance that sound waves can have propagated in the early universe up until the time of recombination. And that's what sets the scale of the acoustic peaks in the CMB power spectrum. And it effectively provides a standard ruler at a redshift of 1100, which we can then go and measure its angle today. Now, there's a problem that if you just use the microwave background alone, then there's a degeneracy in that you can get the same angle for a given ruler length in a flat universe, or for example, a closed curved universe, if you put the ruler further away. So that would correspond to the dotted lines in this picture. So this is an example of what's called the geometric degeneracy. And this limits how much information we can actually get on curvature from the microwave background. But fortunately, we can observe this ruler at different redshifts. So it's also imprinted in the galaxy distribution via what are called baryon acoustic oscillations. And we can use that clustering signal to basically measure the size of this ruler at different redshifts and hence break this degeneracy. There are other ways you can measure curvature as well. It affects the growth of structure on very large scales. It can affect the primordial power spectrum. You can try and estimate the age of the universe as a function of redshift, which will give you constraints on curvature as well. It's worth just pointing out that even if the universe nominally is flat, we always have long wavelength fluctuations from inflation. And if you just do a back of the envelope calculation, you expect a curvature parameter today of about 2 × 10⁻⁵, just from those long wavelength fluctuations. So something between 10⁻⁵ and 10⁻⁴ is the kind of limit that you'd expect to be able to probe with essentially with perfect cosmological observations. Okay, for the primordial fluctuations, in single field inflation, as you know, the primordial power spectrum of the curvature fluctuations is very simple. You've just got some light scalar field, which, at least in the zero curvature gauge, has fluctuations given by the Hubble parameter divided by 2 pi. If you convert those to primordial curvature fluctuations, you get a power spectrum that goes like h squared over phi dot all squared. And this is very close to, expected to be very close to a power law. and it's expected to be very close to a scaling variant power law. So of the form some amplitude and then k over some pivot scale to the scalar spectral index, which conventionally is written as ns minus 1. So n equals 1 is scale invariant. And the reason you expect scale invariance is just because the Hubble parameter is evolving very slowly during inflation. Sorry, there was a question again from Arthur.
Yeah, sorry. So is this, are we already there to exclude curvature of the universe at 10 to the minus 4?
No, we're not. So the current constraints are a few times 10 to the minus 3. In fact, I mean, this 10 to the minus 4 level is actually a very interesting level because, you know, some models of eternal inflation, for example, where, you know, our universe nucleated not that many E-folds before the cosmological fluctuations we observe today left the Hubble radius. You'd sort of expect maybe an omega of about 10 to the minus 4 in such models. Unfortunately, it's going to be really, really difficult to reach that level with cosmological observations, even in the future. So we're not there yet, and I think it'll be very difficult actually to get there in the future. Okay, so the way we probe this primordial power spectrum is essentially by looking at 2-point correlators of observables. So this is just some generic observable O, and ideally you want a linear observable, so it's just something that's proportional to the primordial fluctuations, and then you measure the power spectrum of this, and if you understand the physics of how the primordial perturbation got processed to make this observable, then you can extract information about the primordial curvature. And there's a whole range of measurements that you can, and observations that you can use to do this now, going on the largest scales from the microwave background through galaxy clustering to the smallest angular scales, where, for example, the Lyman alpha forest is useful. Okay, we also expect, at least if the Hubble parameters was large enough during inflation, we expect a background of primordial gravitational waves. And these have a very simple spectrum just given by the square of the Hubble parameter. And again, this is expected to be power law in nature. So you've got some amplitude AT and then some power law with an index NT. And this tensor spectral index is just given very simply by the derivative of the Hubble parameter divided by h squared. And given the Hubble parameter is always falling during inflation, then you expect NT to be less than or equal to 0. So because you're probing the Hubble parameter squared, that's by the Friedmann equations, that's directly telling you about the energy density during inflation. And in particular, you know, you can translate this formula into a constraint on the sort of inflationary energy scale. So the fourth power of that is the energy density during inflation. You know, if just to pick an energy scale of say 10 to the 16 gigaelectron volts, you expect primordial gravitational waves with a power spectrum of about 2 times 10 to the minus 11. And if inflation lasted long enough, you expect the spectrum of gravitational waves to extend over many, many orders of magnitude in scale. And you know, the microwave background can probe these larger scales, and then you know, potentially, although as I'll say later in the talk, this will be very, very difficult. You know, laser interferometers in space can detect these. You know, could hopefully search for the signal on smaller angular scales. Although, as I said, in practice it'll actually be very difficult to do that. Okay, so just to say how primordial gravitational waves actually show up in the microwave background, what you're sensitive to is the fact that if you have a gravitational wave, it introduces anisotropy in the expansionist space, and that produces both temperature anisotropies, shown here by this black line, and this is for a tensor to scalar ratio of 0.01. And it also produces roughly equal power in E modes and B mode polarization. So now with primordial gravitational waves, you don't have this kind of symmetry restriction that you cannot produce B mode polarization. So this B mode, as I said earlier, is a very good channel to look for primordial gravitational waves in the CMB, because if you're relying on, say, the temperature fluctuations, you've got to search for this small signal in the presence of this large background due to scalar or curvature perturbations, and that limits very severely how accurately you can probe the gravitational wave signal from the temperature anisotropes. Okay, another potentially very important probe of inflation is the sort of character of the fluctuations. Are they, for example, Gaussian or non-Gaussian? And of course, the excitement here is that non-Gaussianity is a very sensitive probe of interactions or other dynamics during inflation. So at leading order, we can characterize departures from Gaussianity via a non-zero 3-point function. So if you just take the curvature perturbation for momenta K1, K2, and K3, then the correlator of these is of the form given on the right here. So there's a momentum conserving delta function, which just arises from statistical homogeneity. And then this term, the bispectrum, that depends just on the lengths of the 3 momenta or wave vectors, K1, K2, K3. And different models for the inflationary dynamics, and particularly the action during inflation, will give different forms for this bispectrum. For sort of phenomenologists who are trying to confront these models with data, what we normally do is concentrate on 3 shapes for this bispectrum that bracket most of the possibilities that people have considered. So first of all, there's the local shape where the bispectrum is peaking, where one of the wave numbers is much smaller than the other 2. So it peaks in the sort of squeeze limit. This shape of non-Gaussianity you expect in models with multiple fields, so multi-field inflation. The equilateral shape peaks when the wave vectors are roughly equal, and this tends to arise in models where you have non-canonical kinetic terms in your Lagrangian or other sort of higher derivative interactions. And then we often parameterize the orthogonal shape as well, which just gives us a bit of fine selection between different models within this class. And there are sort of natural targets that you, as an observer, might want to try and constrain non-Gaussianity to. So we normally parameterize this in terms of these parameters FNL, one for each of these shapes. And this is just a kind of little decision matrix for what those observations would tell us. So the key result here is that single field inflation cannot produce local model non-Gaussianity. If you detect FNL local at a level of sort of order 1, then the natural implication is that there were multiple fields that were important during inflation. If if you don't see local non-Gaussianity at the order 1 level, then if you also don't see equilateral or orthogonal non-Gaussianity at that level, that's pointing towards a very simple inflation model where you just have a single field slowly rolling its potential. Whereas if you do see something in equilateral or orthogonal shapes, then that might be pointing to, again, a single field, but now not slow rolling. So, you might have sort of dBi inflation or something, some modified kinetic term in your action that would give then the equilateral shape. So the thing to take away from this is this kind of natural target of FNL of order 1. And what we'll see is that we're not there at the moment in terms of reaching these levels, but with future large-scale structure measurements, there are reasonable prospects that we'll be able to probe local model non-Gaussianity down to this sort of critical threshold. Whereas for the other shapes, it will be very, very difficult. I mean, nothing has been proposed at the moment that will reach down to these levels for equilateral or orthogonal. Just a quick word about how you actually then go about constraining non-Gaussianity, for example, from the microwave background. From a theoretical perspective, you start with the primordial spectrum, bispectrum. You apply the usual CMB physics to get something that's observable. So this would actually be the bispectrum of the CMB itself. And this now has this sort of beautiful acoustic peak structure appearing in it through this transfer function. And then you can go and confront this with observations. So you take your microwave background maps, you essentially measure 3-point correlators. So you can think of this as measuring the correlation between 3 points forming a triangle. And in practice, we take the multiples of the map, form some estimate of the bispectrum, and then confront it with our expectations. There was a very important paper in 2008 by Neil Dalal and others that pointed out that there was a very interesting effect in large-scale structure that was also a very powerful probe of local model non-Gaussianity. This is called scale-dependent halo bias. And the way this works is as follows. So local model non-Gaussianity, you can, one very simple sort of model that gives rise to non-Gaussianity of this form is if your primordial curvature fluctuation, we normally use in the large scale structure literature, usually use the quantity phi, which is actually the gravitational potential in the matter dominated era, but it's just related by a factor of 3/5 to the primordial curvature perturbation. You write this as a Gaussian field phi, and then FNL local, and then the square of that Gaussian field. And this is essentially minus the Newtonian gravitational potential, is what phi is. So if you just sort of take the short scale modes of the density fluctuations that are implied by this formula, you find that the short scale density perturbations of the full field are basically those of the Gaussian field, and then 1 plus twice this non-local non-Gaussianity parameter, and then the long wavelength modes of the phi field. So what you can see is that this long wavelength mode of little phi is going to modulate the power in the small scale modes of the density fluctuations. So this is just illustrated with these little plots on the right here, where I've got a large scale mode and then some small scale modes superimposed on top of it. And in the Gaussian case, where FNL local is 0, you just see equal power in the small scale perturbations, both at the peaks and the troughs of the large scale mode. Whereas with positive local model non-Gaussianity, you get more small scale power at the peaks of the large scale mode and less at the troughs. And given that halos are going to form at the peaks of the density field, what you'll find is that you'll have lots of halos here, very few halos here, and the halos will be more clustered on large scales in this model than they would be without local model non-Gaussianity. So in terms of the power spectrum, what that means is that you essentially get excess power, and in particular, it appears like a form of halo bias that has a very characteristic scale dependence, going like 1/k². That's just because of the Poisson equation relating density fluctuations to phi. So the solid line here is showing a Gaussian model, and then if you have a very large local model non-Gaussianity of 500, you get all this excess power on large scales.
Sorry, is the sign arbitrary or known? What do you mean by arbitrary? I mean, a given model will predict a given sign, yes. But both signs could be present in various models. There's no fundamental bias towards one side.
Yeah, that's right, I think.
Thank you.
Okay, the other sort of property in terms of the character of the primordial perturbations that we might want to think about is whether there's any evidence for isocurvature modes. So the idea here is that in single field inflation, then you've just got a single field, which when the universe reheats, will just decay into the standard model particles. And there's no mechanism thereby that you can produce relative fluctuations in the number of particles. So in particular, particle species I, will have no relative fluctuations compared to, say, the photons. Whereas if you have multiple fields during inflation, then it's possible to produce non-adiabatic initial conditions, or what we call isocurvature modes. And these are just relative fluctuations in the number of species in such a way that the relative numbers kind of compensate each other to give no gravitational or metric perturbations in the primordial universe. So these are normally characterized by gauge invariant amplitudes like this one here between, for example, say the cold dark matter and the photons. And this amplitude is just given by the difference of the fractional fluctuations in the cold dark matter number density, photon number density, or in terms of energy densities, just delta C minus 3/4 delta gamma. So the picture here would be, in the early universe, that the photons are dominant, they're the dominant energy density, and they have an absolutely tiny density fluctuation. And then you have a larger fractional fluctuation in the cold dark matter. And the net effect of adding the two together is that there's no total density fluctuation or curvature fluctuation. And depending on the model, these isocurvature fluctuations can generally be correlated in some way with the curvature fluctuations. So you can propagate these initial conditions through to the micro background power spectra. And this is just an example showing, for example, in this mode, where you have these fluctuations in number between the cold dark matter density and the photons. The black line here is just showing what the power spectrum would look like for a scale invariant spectrum of these initial fluctuations. So the key thing here is that just because of the way the transfer functions work in these isocurvature models, the power is really all on large scales, and it's suppressed by transfer effects on small scales. And you get similar things showing up in the polarization as well. Okay, so let me now review a little bit what the key data sets are that we use to make constraints, and just talk a little bit about what the current sort of state of the art is on our observational constraints on inflation. So statistically, the most important data set we have at the moment from the micro background is from Planck. Many of you will have heard many Planck talks in the past, so I don't really need to introduce this, but it was a mission that was launched in 2009. It operated for about 4 years. It was a significant improvement over WMAP in terms of both resolution and sensitivity. It had 9 frequencies, 7 of which were polarization sensitive. The data that Planck produced ultimately were these temperature maps in 9 frequencies going from 30 gigahertz to 857 gigahertz. And what you can see in all of these, the bright band across the center is just emission from our galaxy. And at 30 gigahertz, the dominant emission process is actually synchrotron emission from electrons spiraling in the galactic magnetic field. Whereas at high frequencies, predominantly you're seeing thermal emission from dust grains that are heated by starlight. These 3 middle channels from 100 to 217 gigahertz are the channels that we ultimately use for cosmological constraints. You can certainly see at 217 there's significant dust contamination, whereas at 100 and 143, it's much more concentrated towards the galactic plane. So what we do in practice is sort of mask these channels reasonably aggressively. Potentially, we can also clean the 217 gigahertz channel by subtracting some of these higher frequency channels to try and remove the effects of dust, and then look at the statistics of these maps outside of the masked region. So, this is just a famous plot of what the power spectrum, looks like from Planck. The data points here are the measurements. The blue solid line is a fit for the lambda CDM, sort of inflationary inspired model, giving this beautiful fit to the measured data. And the bottom is just showing the residuals of the data around that model. Planck also measured polarization in 7 channels going from 30 gigahertz to 353 gigahertz. So it produced full sky maps as shown here. So this is the Q and U Stokes parameter, and then the magnitude of the polarization. And again, at the lowest and highest frequencies, you're dominated by galactic emission. But at the intermediate frequencies, you're starting to see that the microwave background signal actually poking through. Planck didn't really have very good sensitivity to measure the small polarization signal. But in some parts of the sky where the Planck scanning meant that that region of the sky was revisited many, there was deep integration on that region. You can make quite high signal to noise images. And this is just one example showing the temperature fluctuations in the color scale. And then the little sticks, the little rods, are the direction of polarization. And you can see a quite nice high significant measurement here, polarization.
Excuse me, may I ask a question?
Yeah, please do, yeah.
Regarding these maps, as you said, for the real analysis, the galaxy is always screened out, blank, masked out. Nevertheless, they do publish full sky maps of CMB only. How do they do that? Do you know?
Yeah,
curiosity.
So you basically just combine together this multi-frequency information to subtract out the galactic emission. So this map at 857 gigahertz is essentially all galactic dust. So if you subtract off some small fraction of this from the 100 gigahertz map, then if you get that fraction right, so if you understand the spectral energy distribution of the dust emission, then you can remove dust from this. And similarly, if you subtract out some of these lower frequencies, you can subtract out synchrotron and other effects, leading to these nice images like I showed at the start, which are basically just the microwave background.
But they're not actually used for the fits, right? They
are used for
the galactic plane
analysis. So, for example, the biospectrum analysis and gravitational lensing analysis, for example, did use foreground cleaned maps. Most of the 2-point analysis did not, although there actually have been some subsequent analyses that have used cleaned maps to some extent as well.
Okay, thank you.
Okay. So if you take those measurements of polarization from Planck, you can measure their power spectra. So on the right here, this is the E-mode auto power spectrum, and on the left, the cross correlation with the temperature. And as I said, the measurements are not as precise as they are for the temperature anisotropies, but you can still see very nice agreement between the theoretical prediction, which is the blue line, and the data points. And it's important to note here a couple of things. The solid line here is the lambda CDM model, but it's calibrated on the temperature data. So it's not necessarily a fit to this polarization data, but you still see very nice agreement. The other point to make is that the polarization analysis is difficult. There are various choices that you make in the analysis related to calibration, choices of masks and things that do lead to small differences in the polarization only results from Planck, depending exactly on what choices you make. So the papers often present results for various different likelihood choices, depending exactly on what analysis choices you're making here. When you combine in the polarization and the temperature fluctuations tend to dominate, and these analysis differences become much less significant. But you should just be aware that there are minor differences depending exactly on your analysis choices. Since we published the Planck final legacy papers in 2018, there have been some developments afterwards. So I just want to show this from my colleague Georgia Stathiou and Steve Gratton in Cambridge, who've been working on sort of squeezing more out of the Planck. So this is the power spectrum from Planck using their own analysis, but essentially it's very close to the results from the published 2018 results. And then what they tried to do was squeeze a little bit more out of the data by being a little bit more aggressive, so keeping more of the sky when you do the galactic masking, doing some mild foreground cleaning to try and compensate for that. This is the spectrum that you then obtain. And okay, it's not by eye, it's not, you know, it's perhaps hard to see these differences, but if you focus on the residual panels at the bottom, you can really see that things are cleaning up, and you know, there's significantly less scatter in these new results as a result of the greater sky fraction. And the reason this is important is not really because you know, we want the very minor percentage increase in precision of cosmological parameters that you would get from this sort of analysis. The important thing is that, you know, that there are some features in the Planck data that appear to be a little bit anomalous, and I'll discuss them a little bit later. What you would hope is by squeezing the data further, you know, you might be able to get a handle on whether those fluctuations are just statistical fluctuations, or whether there's actually something going on in the physics that we haven't accounted for, or some systematic effect. And you know, the basic idea here is that if it is a statistical fluctuation, if you add in some independent data, you would expect to be taken towards the truth as you add in more independent data, and that the apparent anomaly will become less significant. And in fact, for Planck, that is the case for most of the sort of slightly anomalous features. Okay, we also have data from ground-based telescopes. So the Atacama Cosmology Telescope, this is a 6-meter telescope observing in Chile. It's gone through various incarnations over the past 10 or so years, but its latest camera is called Advanced ACT. It has 5 frequencies. It's surveying 40% of the sky. And it will produce, when it's finished at the end of this year, it will produce maps in polarization that are 5 times more sensitive than Planck. This is just an example of some of the maps that have currently been released from ACT. So this is a small region of the sky, 630 degrees squared at 100 gigahertz. Temperature shown at the top, and then the Stokes Q and U parameters at the bottom. And what you can see from the kind of directional correlations in these Stokes parameter maps is that you're seeing very high signal to noise measurements of the polarization here. So significantly more sensitive than Planck. We also have the South Pole Telescope. So this is a 10-meter telescope operating at the South Pole. Again, it's gone through various incarnations, but its latest version is called SPT-3G. It's observing at 3 frequencies. Being at the pole, it can't observe the very large sky areas that ACT is able to observe. So instead, it's focusing on 1500 square degrees. Its final map polarization depth will be about 15 times that of Planck. But you have to trade that off against the smaller sky area when you're assessing the statistical significance of the results. And then finally, for the micro background, we've got this BICEP Keck series or family of experiments that have been operating at the South Pole from 2006. So these are very different to the South Pole Telescope and ACT telescopes in that they're very small aperture, sort of half-meter telescopes, targeting degree scale B-mode polarization. And the BICEP team have been absolutely relentless at sort of staring at the same patch of the sky, sort of 600 square degrees for 15 years now. And in their latest version of the experiment, they've now got 6 frequencies and about 30,000 detectors, or at least it will have when it's completed in a couple of years' time, observing this low region, this region of low galactic emission to try and search for primordial gravitational waves. So sort of putting all those things together, the power spectrum measurements that we've now got are shown here. This is just a compendium from one of the recent ACT papers. You've got the temperature power spectrum at the top with data points from the various experiments, E mode polarization, and then B mode polarization at the bottom. We haven't yet detected primordial B modes. What you're seeing here is this gravitational lensing signal that I mentioned earlier, which has now been detected at high significance by these experiments. So what you should take away from these plots are that, first of all, the exquisite fit of the data now extending to small angular scales with these ground-based experiments. Much of the work has been done in the temperature fluctuations. We're reaching the measurements of cosmic variance limited now to scales where astrophysical extragalactic foreground emission becomes very important. So really to make progress with, for example, inference from the power spectrum of the microwave background, the polarization is going to become much more important because there's still significant improvements that can be made in reaching the cosmic variance limit in the E mode polarization. And we just expect extragalactic foregrounds to be much less significant for polarization. So you can push to smaller angular scales, higher multiples in this plot, and still not be confused by extragalactic emission. And of course, what we're desperately searching are the primordial signal from B modes way down here in this plot on large angular scales. For what I'm going to say a little bit later about curvature constraints, it's worth just saying that we can, from the microwave background, we can also extract information about gravitational lensing. So lensing leaves sort of subtle distortions in the microwave background that we can extract. And this allows us to make maps of essentially all the matter in the universe, albeit at very coarse resolution, but integrated all the way back to the last scattering surface. So this is what we get from Planck, which is a very high significance 40 sigma measurement of this lensing effect. And then more precise measurements, but over a small region of the sky from the South Pole telescope. And you can take these maps, take their 2-point function or power spectrum. For Planck, that's the grey error bars here. For SPT pole, it's these red points. And you can compare it to what you would expect for this lensing signal from your Lambda CDM model, calibrated on the CMB fluctuations that were sourced at the time of last scattering, so in the early universe. And the fit is really fantastic. What we see at late times is in CMB lensing, at least, is consistent with what we would infer from the microwave background at earlier times. The key point I want to make in this is that if you change the curvature of the universe, in particular if you go to a closed model, you tend to increase the lensing power, and if you go to an open model, you tend to reduce the lensing power. And this is a way that we can actually break this geometric degeneracy I mentioned earlier and learn something about curvature from the CMB itself. We also have a wealth of large-scale structure data. This is just examples from the Sloan Digital Sky Survey, operating for many years now and gone through various incarnations, the most recent being the extended baryon oscillation spectroscopic survey. This was a spectroscopic survey that recorded the locations and spectra of many galaxies. And then you can use those galaxies to perform clustering measurements. And for example, these are just some power spectrum measurements showing what we call anisotropic clustering. So this is the effect of peculiar velocities, what we call redshift space distortions, giving apparent anisotropic clustering when you observe galaxies in redshift space. By making measurements like this, it's actually a very nice way to learn something about the growth of structure in the universe. You can also use the baryon acoustic oscillation feature in these clustering measurements at different redshifts as a standard ruler that you can then try and make curvature measurements with. And the final probe that I just want to mention is the Lyman Alpha Forest. which, as I said earlier, is absorption by neutral hydrogen in the Lyman alpha line of the sort of continuum emission from some background quasar. So you've got some background quasar, the light from it passes through all the intergalactic medium in front of it. You take the spectrum of that quasar, and this is an example of that spectrum with wavelength on this axis. Here's the Lyman alpha emission from the quasar itself, and then shortward, at shorter wavelengths, you get this kind of forest of absorption lines corresponding to absorption by neutral hydrogen at different distances in front of the quasar. So by making correlation measurements on these fluxes, you can probe the clustering properties of neutral hydrogen, and hence the matter. And the reason this is important for cosmology is you can, you're doing things at relatively high redshift because quasars are bright, so you can see them to very high redshift. So you can measure this clustering at high redshift, and that allows you to access small scales that are still in the quasi-linear region. The modeling you can essentially do from first principles to understand what the statistics of these fluctuations should be. Okay, so I think now is probably an appropriate time to pause. I've talked for about 50 minutes. What I suggest is we perhaps just take a break or take some questions for a few minutes, and then I'll discuss what our current constraints are from these data sets and future prospects in the second half of the talk, if that's okay. Arthur, did you want to ask a question?
Yes. Yeah, may I ask again? I have a question concerning this small scale spectrum that you get from clustering, as you just explained, and the larger distance scale that you get from Planck or from the South Pole Telescope. Is it sensible to put them in one plot? I mean, can you make one plot with normalization known between the two? I've never seen such a plot, or not recently. I would like to know whether this is understood well enough to plot them, so to speak, in one picture.
Yeah. So yes. I mean, you can. Do
you have a plot like that to show us?
Yeah, I did show one actually. Let's just. Yeah, can you see that? Is that
small? But I can roughly. Yeah. Okay. Great. Thank you.
Yes. I mean, of course, what you have to do in these plots, what this is a plot of, it's not the primordial power, it's the matter power spectrum that's kind of inferred from this whole range of observations. But yeah, going all the way from CME observations here through galaxy clustering through to the Lyman alpha forest.
And there's no fudge factor in the normalization of the Lyman alpha forest, say, versus Planck and what is that? There's a cosmic. What does cosmic shear mean?
So cosmic shear. So that's weak gravitational lensing.
Okay.
No, I mean there are of course calibration factors in all of these experiments that you have to deal with, and they're only known to a certain level of precision. So I guess if you're actually doing the cosmology,
can you? I mean, in principle,
sorry, I didn't.
In principle, there would be a huge handle, a huge lever arm. How do you say to measure something like the running of the spectrum, the running of the spectral index?
Indeed, yeah, and we'll talk about
that. Affected by this possible normalization factor. So how much can one hope that progress will be made in that respect?
Yeah, so you're absolutely right. There is this very large lever arm in terms of scales, and I'll show some results later that actually attempt to do this, sort of combining small scales and large scales. In principle, if you've understood the calibration of your observations correctly, then there are no fudge factors at all. Although in practice, we only know calibrations to finite accuracies, so we have to sort of marginalize them out in these comparisons. particularly with the Lyman alpha forest and combining with the CMB, essentially both observables you can predict, from first principles. So that there shouldn't be kind of any adjustable factors. Although the Lyman alpha measurements are difficult because we have uncertainty in the quasar continuum, which introduces a level of uncertainty.
Okay, thank you. So you will come to that later. You will show us some.
Yeah, I can show you some results.
Good, thank you. Perfect. Anthony, are 21 centimeter measurements part of this?
So are they part of
part of the tools that you can use to measure perturbations at small scales?
Yeah, absolutely. I mean, we don't have any measurements yet from 21 centimeters surveys.
Will it come soon, or what's the time scale?
So I mean, most of the focus so far has been actually on the reionization epoch. So trying to understand reionization with 21 centimeter, and again, there's no detections yet of the signal from reionization. But I mean, there are so I mean, in terms of timescales, there are missions like Spherex, which could be launching in 2 or 3 years' time, actually, which are essentially trying to do the same thing. So use essentially the integrated emission from all galaxies and look at the clustering in that signal. So very much like intensity mapping. Yeah, I think there the interest really actually is in non-Gaussianity rather than, I think that's really where the breakthroughs will come from those surveys, actually, rather than improvements in small scale power measurements. Looking sort of further ahead, yeah, you could certainly hope to do, I mean, the real hope would be to be able to do 21 centimeter from the dark ages, so from the period before reionization. The problem there is it's redshifted to such low frequencies that you just can't do that from the ground. So there are ambitious plans to do things on the far side of the moon, for example, so you can actually access these super pristine fluctuations over this enormous volume that's accessible but that's many decades away, I think.
Okay. I somehow had the impression that it was something coming soon, but maybe I had the wrong idea of timescales. Yeah.
It depends what redshift range you're talking about. I think so. 21 centimeter up to redshift 6. Yes, that's a shorter timescale, definitely.
Okay, good. And what are the names of the important experiments and missions there, which one has to watch out for?
There's so I mean things that are probing the epoch of reionization. That's things like Hera, Chime. In terms of sort of post-reionization, there are things like, I mean, again, they're mainly focused on BAO scales, so much larger scales than you might be interested in. But things like Bing.
Power spectrum before 6 go non-linear. That was my expectation, that people could do that.
Yes, that's right. Yeah, but but in terms of the actual scales that you're probing, most of those experiments are actually focused on BAO scales, so very large scales actually.
Right.
I
see.
And then there are proposals like there's an experiment called Puma that if I get time, I can mention at the end of the talk, which looks very promising for non-Gaussianity actually, and that's an intensity mapping.
Okay, thank you.
Okay, should we start again? I'll try and wrap up in 50 minutes if I can. Okay, can you see that okay?
Yes, we can see.
Yep, great. Okay. Okay. So, so in this second half, as I said, I'll having reviewed, what the observations are that we're using and the motivation. Let's actually look at what the results are and what the prospects are for improving them in the future. So let's begin with spatial curvature. So this is actually an area where there's been a lot of interest recently, a lot of debate, and all this is fueled basically by the fact that if you just look at the Planck data alone, so the power spectrum data, there's moderate, at moderate significance, a closed universe is favoured. So this is showing omega matter and then the curvature parameter omega k, and the coloured regions and these sort of contours I'm outlining here are from the temperature and polarization power spectra. And you can see that there's a very significant degeneracy here, which is this geometric degeneracy I mentioned earlier. But the allowed region does extend significantly into the region of parameter space corresponding to curve models. And the best fit is curved at the few percent level. However, if you bring in the CMB lensing data that I showed you earlier, or the baryonic acoustic oscillation measurements from galaxy surveys, then you're pulled back towards flatness. So lensing takes you to these sort of regions, and BAO very precisely takes you back to a flat universe. So an omega k of 0.0007 plus or minus 0.002. So that's a measure of flatness at the 0.2% level. And you can actually see this quite strikingly in this very nice plot from the EBOS collaboration. So this is just comparing for BAO measurements, what the prediction would be relative to the flat lambda CDM model of that best fitting curve model from Planck. So the red dashed line here is, for example, how the perpendicular BAO scale, so that's essentially the angular diameter distance, would look as a function of redshift relative to what it is for the best fitting flat model. So the red line is that model ratio, and the data points are the ratio of the data to the flat model. And what you can see is it's very strongly ruled out. The BAO data, does not want this very significant curvature. And the same is true for supernovae data. You can do the same thing with luminosity distance, and again, it's strongly disfavored. The interpretation then, I think, is that certainly most of us in Planck agree on, is that essentially it's like a statistical fluctuation in the full sky temperature spectrum is pulling you towards closed models. And that then is strongly disfavored by CMB lensing, BAO, and supernova data. One point that Georgia Stathiou and Steve Gratton made last year, which is worth just pointing out again, I think, is that because of this strong geometric degeneracy that you have with the temperature power spectrum and the polarization power spectrum when you're trying to measure curvature, you have to be very careful with the posterior distributions that you actually infer and how you interpret them on curvature, because the choice of prior is very, very important. And the priors for curvature are not not really well motivated. In particular, a uniform prior on omega k is not really well motivated at all. It's difficult to interpret these posterior distributions. If you take the CMB plus BAO constraints on curvature, so curvature at the 0.2% level, if you turn that into a constraint on the curvature scale, what you find is that the curvature scale defined by A naught over root of the curvature scalar has to be bigger than about 80 gigaparsecs, so significantly larger than the current horizon. And in terms of inflation, if we say that, say, omega k is of the order of 1 at the start of inflation, then you can use constraints on curvature, obviously to put constraints on the amount of e-folds of inflation, the total number of e-folds. And if we express these in terms of this parameter n star, which is the number of e-folds before the end of inflation at cosmological scales left the Hubble radius during inflation, then the total number of e-folds needs to be at least 5 times, at least 5 e-folds more than n star. So there must have been at least 5 e-folds of inflation before our modes that we observe today left the Hubble radius during inflation. Let me just say that there has been, as I said earlier, quite a lot of discussion and different viewpoints expressed about how to interpret these curvature measurements from Planck. And if you're interested in seeing some of the alternative viewpoints, the papers by Elena Di Valentino and Will Handley are worth looking at. Okay, what about the primordial power spectrum? Since the measurements from WMAP and through the various releases from Planck now, we've had very strong evidence that the primordial curvature fluctuations have a spectral index that is less than 1, so NS of about 0.965. The measurement now is so precise that, at least within the context of the model that we're working with, scale invariance is very strongly ruled out. So there's a delta chi-squared of 70 between the best fitting model with this value of NS and a scale invariant model with NS is 1. And this is just shown graphically in this plot here, showing the blue line is the best fitting NS equals 1 model, so the scale invariant model to the Planck data, and the red line is the best fitting model where you allow the spectrum to have an arbitrary tilt. And clearly the NS equals 1 model is strongly disfavored. The data is good enough now that, at least within the range of models that we normally consider, so things like curvature, additional light, relativistic species, the constraint on NS is actually quite robust to those assumptions. And furthermore, there's no evidence now from the CMB data for any running of the spectral index. So this is something that the long lever arm of Planck has really helped with. A decade ago, or perhaps a bit more, that there was some evidence from small-scale ground-based CMB experiments combined with satellite measurements on the larger scales that there was some running. But now, with a nice uniformly calibrated spectrum across all these scales from Planck, that evidence has now gone away. And in particular, there's no evidence for running, so the second derivative of log p with respect to log k, or running of the running either. They're both consistent with 0. One of the very nice things you can do with the CMB data is make sort of quasi-independent tests of things in the temperature power spectrum and the polarization power spectrum. So these are just showing NS against various parameters, something that measures the amount of clustering, S8, omega matter, and H0. And the red contours here are constraints from the temperature power spectrum, and the gray are from the cross-correlation of temperature and polarization. And there's 2 different analyses here. The one on the left is very similar to the published Planck 2018 analysis. The one on the right is this Eustathiou and Grattan analysis that squeezes a little more out of the data. And what you can see, particularly if you focus on the right-hand panels, is the really nice agreement now between the temperature and the polarization measurements, and hence constraints on NS. So yeah, really nice agreement from this quasi-independent observable, which is the polarization. One of the recent things that's been happening with the large-scale structure data is attempts to actually use the broadband shape rather than just things like the BAO features in the spectrum to constrain cosmology. And this is actually what people used to do in the old days with galaxy power spectrum data. But now, given the precision of the data and the range of scales that are being probed, it's required a lot of new technology to be able to do these sort of analyses. So what goes into this are, on the theory side, you need a good description based on effective field theory of large-scale structure to understand the quasi-linear scales that are involved. You need to be able to evaluate models very quickly as you move around parameter space. So that's doing loop integrals very, very efficiently and so forth. But there've been, a couple of groups have made great progress on this in the last year or so. So this is using BOSS, the BOSS galaxy samples and using power spectrum measurements from BOSS. And the main interest here actually was in the Hubble parameter rather than the primordial power spectrum. But the constraints on NS, although they're much weaker than you get from the CMB, they're still consistent with what we see from the microwave background. And it's a nice independent confirmation of a departure from scaling variance. Okay, we also had a question earlier about the Lyman alpha forest, which is probing the fluctuations on much smaller scales than the microwave background, and what that tells us about the primordial power spectrum. This is an analysis based on the 14th data release from SDSS. So this doesn't use all of the data that is actually available. It just uses a subset of the quasar data in EBOS. So these constraints will change and improve with an analysis of the full data set. But what you basically do is, you're taking measurements of the Lyman alpha forest power spectrum at different redshifts, and then using that to constrain cosmological parameters. And these are showing plots of omega matter against NS for various data choices. In particular, the usual Planck results are shown in blue here, and then the constraints from the Lyman alpha data are shown here in red, for the case where you assume a power law spectrum for the primordial fluctuations. And what you can see is that there's a certain amount of tension between these measurements, with the Lyman alpha data preferring a lower omega matter and a somewhat lower NS. Just as an example of a phenomenological model that actually fits this data much better, if you assume a broken power law, so on CMB scales you assume some spectral index, and then you assume a different spectral index on Lyman alpha scales, you actually get a significant improvement in the chi-squared. So it improves by 14 with one additional parameter. So that's quite a significant improvement. And that's shown in this plot, where these sort of contours are what the CMB wants, and these contours are what the Lyman alpha forest data wants. So it wants a somewhat redder, Lyman alpha wants a somewhat redder spectrum than CMB. And of course, if you then allow for running in your spectrum, then you are pulled towards negative running because of this kind of mismatch between the spectral slopes that the two data sets want. If you just combine these at face value, you get pulled to negative running in this form. What it is worth saying is that neither data set alone, though, actually wants running. So over its given range, which the CMB is probing or Lyman alpha is probing, each of those data sets on their own don't want running. it's only when you combine the two that you do, because essentially of this sort of slope mismatch between the two. So it's not clear what's going on here. Maybe this is super exciting and this is new physics, or maybe there's just some interpretation of systematic problem, particularly with the Lyman alpha analysis, which is still at a fairly it's not as mature as analysis as with the microwave background. But I think this is something definitely to watch out for, and it'll be very interesting to see what happens in future data releases. Well, not when the final DR16 data is actually analysed for the Lyman alpha forest clustering. Okay, the other sort of thing you can do is to make non-parametric reconstructions of the primordial power spectrum. So these are just examples from Planck, and the idea here is you basically assume that the power spectrum is described by a number of points. So you give the power at a number of different scales, and then you try and join them up smoothly with some splines or something, and then you allow these points to freely vary. And in fact, in this analysis, you allow the number of points and their locations to vary freely. So if you just have 2 points, then you're just fitting power law spectra. As you increase the number of nodes that you allow in these reconstructions, then interesting things kind of start to happen, particularly on large scales. You start to see some favoritism for models with less power on large scales. However, if you kind of marginalize over the number of these nodes that you're allowing in the reconstruction, you end up with this sort of final marginalized result for the primordial power spectrum. So this is kind of showing allowed regions at a given scale of the primordial power. And there really isn't any significant evidence in this marginalized plot for deviations from scaling invariance. So it's just dwelling a little bit on this feature here that you get when you add more knots or nodes. And this is just the well-known deficit of power that there is in the microwave background power spectrum at around L of 20. There's this little dip in the residuals, and what's happening here is that in these non-parametric reconstructions, it's locking onto that dip and trying to suppress primordial power on those scales. So again, this could be indicative of something interesting in the dynamics of inflation on those particular scales, but more likely it's just a statistical fluctuation that is present in the data. And this is one of the things where better polarization data on these scales will be interesting, because that will give us a kind of independent handle on whether there is anything going on in the primordial spectrum on these scales. Okay, let me move on to constraints on primordial gravitational waves or tensor modes. So, as I said at the beginning, we haven't yet detected tensor modes in the CMB. This is just showing current constraints on the tensor to scalar ratio at some particular scale and the scalar spectral index. So this is a kind of nice phenomenological plane in which to view inflation. The red contours here, or very similar to the green contours, are just using the temperature and E mode polarization power spectra from Planck. And you get a constraint that the tensor to scalar ratio is less than about 0.1. And this is interesting because this constraint is about as good as you can actually do with the temperature power spectrum. Remember I said at the start, without using B mode power, you're always trying to subtract out the much larger contribution to the temperature fluctuations on large scales from curvature perturbations. And that limits how accurately you can constrain primordial gravitational waves. And the Planck data, being cosmic variance limited on these scales, is essentially saturated this band. It's a little bit model dependent as well. So if you allow, for example, running in the spectrum, then that will reduce the contribution from scalar perturbations on large scales and weaken this constraint on R. And similarly, if you remove the very low L temperature data, where there's this funny feature that we were just talking about, if you remove that, then your constraints also weaken a little bit. However, none of this really matters because we do have B mode measurements now. This is just a compendium of all B mode power spectrum measurements that we have. And the most constraining on the relevant scales for primordial gravitational waves are from the BICEP and Keck array experiments. And although they haven't detected anything, their upper bounds are very constraining and give rise to this blue region in this plot, which I'll discuss in a second. Just before we do, let me point out that these measurements, these upper limits here, now include multi-frequency cleaning, which of course is very important. So just to remind you how this works, if you look at the BICEP 2 Keck array measurements at 150 gigahertz, there is a significant evidence for B modes, but we now know they're not primordial in nature. And we know that because, for example, the Planck data at 353 gigahertz, if you process it in the same way to correspond to what BICEP would actually observe, you can then compare what's observed at 150 with 350 gigahertz. And what you see is that these are actually rather strongly correlated. And if you subtract out this signal, then your measured power, which was originally given by these black points before the dust cleaning, once you subtract out your estimate of galactic dust polarization from these higher frequencies, you get the blue points, which are just consistent with the gravitational lensing signal, with no evidence for primordial B modes anymore. Okay, so if you include the B mode data, your constraints now become much less model dependent and rather tighter, and the tensor to scalar ratio is now constrained to be less than 0.06. The implications of this for inflation, well, remember the amplitude of the gravitational wave power is just given by the Hubble parameter squared, so you can convert this into a constraint on the inflationary Hubble parameter. That's 2.5 times 10 to the minus 5 in Planck units, or equivalently the energy scale of inflation being less than 1.6 times 10 to the 16 gigaelectron volts. Okay, the implications of these measurements, sorry, for single field inflation. One way to think about this is whether you can test this single field slow roll consistency relation that you would have in single field models with canonical kinetic terms, where the tensor to scalar ratio R is just -8 times the tensor spectral index. So in terms of trying to test this, it's extremely difficult. This is a plot from the Planck inflation paper showing R against the tensor index NT. And the blue contours here are constraints that you get from combining the Planck power spectrum measurements and the B mode measurements from BICEP. And the relation you're trying to test is, well, it would lie, these single field slow roll models would lie on this dashed line here, which on the scale of the plot is indistinguishable from the NT equals 0 line. So there's no evidence for inconsistency, but the test is clearly very, very weak. One thing you could try and do is to tighten up constraints on the tensor spectral index by using constraints from LIGO on constraints on the background of primordial gravitational waves. So just their constraints on a stochastic background on a frequency of 20 hertz. That corresponds to a sort of a density parameter for gravitational waves, less than 2 times 10 to the minus 7. So, if you make the assumption that this power law NT holds all the way over 18 orders of magnitude in scale, then you can use this constraint to cut out some of these regions of parameter space where you have a rather blue spectrum and would actually over-predict the levels that are seen by LIGO. And things then tighten up to this red region. I think this is nice for illustration, but it's of course really dangerous and very model dependent, extrapolating over such a large range of scales. Okay, just very briefly, constraints on isocurvature modes. I mean, I can be very brief here because there is no evidence for isocurvature modes. This is just showing posterior distributions for the fraction of the temperature power that could be contributed by non-adiabatic modes for different kinds of isocurvature initial conditions. I mean, the take-home message from this is that less than about 2% of the contribution to the variance of the temperature fluctuations can come from non-adiabatic modes. So no evidence for anything other than adiabatic fluctuations. Okay, non-Gaussianity. As I said earlier, the bispectrum is the most sort of natural way to try and confront primordial non-Gaussianity with observations. These are just nice renditions from the Planck non-Gaussianity papers of what in our universe, the bispectrum actually looks like as a function of L1, L2, and L3. You can do this for temperature or you can do it for polarization. And of course, one of the sort of very disappointing things for many theorists was that the Planck results really showed no evidence for non-Gaussianity. So the constraints on temperature are shown here on the left for the local equilateral and orthogonal models. These improve somewhat, and in some cases quite significantly, if you include polarization data. But unfortunately, they're all consistent with zero. I should say that there are various contaminants that you have to correct, particularly in the local model, to make these constraints. I don't have time to go through the details of this, but we think we understand how those contaminants act and are reasonably confident in subtractions that are made. Okay, I mentioned earlier that you could also constrain non-Gaussianity, at least in the local model, by looking for this scale-dependent halo bias on large scales. So this bias of galaxies that goes like 1 over k squared. You know, this has been attempted for several data sets now, and this is just the latest from the clustering of EBOS quasars. The reason you want to use quasars is because you can see them to high redshift, so you can access large volumes. And also they're highly biased traces of large-scale structure, which tends to amplify this non-Gaussian signal. So here are the power spectrum measurements that you want to use. And remember, what you're looking for is a kind of upturn on large scales due to this scale-dependent halo bias. The constraints are shown in this plot. So this is FNL local, plotted against the Gaussian quasar bias. And you know, there's a certain degeneracy between these two parameters, but the marginalized constraints on local non-Gaussianity are that it's between -51 and +21. So significantly weaker than the CMB constraints at the moment, which have an error bar of about 5. But again, this is only using a subset of EBOS quasars, and the prediction for the full data set is that the error might come down to about somewhere between 5 and 8, which is getting very close to the CMB constraints, actually. So this is really showing you know, the promise that this method has, particularly for local non-Gaussianity. Okay, so let's just take stock of where we are then in terms of implications for the dynamics of inflation. So the fact we don't observe non-Gaussianity, we don't observe isocurvature modes, suggests that you know, our initial fluctuations were consistent with the predictions of single field slow roll inflation. And such models are usually parameterized in terms of the Hubble slope roll parameters. They just tell you about the evolution of the Hubble parameter during inflation. So epsilon1 is minus h dot over h squared. Epsilon2 is like the logarithmic derivative of epsilon1 divided by h. And the predictions are that, as you well know, if you have a canonical kinetic term in the Lagrangian, the scalar spectral index is given by this combination of the slow roll parameters. The tensor to scalar ratio is 16 times this parameter, and the tensor spectral index is minus twice epsilon1. And combining these two together gives you the inflationary the tensor consistency relation, R is minus 8 nt, that we discussed earlier. Okay, so in terms of constraints on these parameters, these are just plots again from the Planck inflation paper showing constraints on epsilon1 and epsilon2. So this is a kind of linearly distorted version of those RNS plots that we were showing earlier. What you can take away from this is, the fact that we haven't seen gravitational waves gives you an upper bound on epsilon1, and then the measured spectral index gives you measurements of epsilon2. And the fact we haven't seen gravitational waves means there's a kind of hierarchy between these parameters now. So epsilon1 is much smaller than epsilon2. And if you translate that into what that means about the shape of the inflaton potential, then if you work in terms of these potential slow roll parameters, so the first one is just the slope squared of the potential. The second one is measuring the curvature of the potential. They're approximately related to the horizon flow parameters epsilon1 and epsilon2 in the following ways. So you can transform plots like this into plots on these potential slope and curvature as follows. And what you see is that the data now favors this region where the second slope roll parameter is negative, corresponding to the second derivative of v being negative. So you have these sort of concave type potentials being favored. Okay, so sort of putting it all together, this is this very famous plot that you'll have seen many times, showing tensor to scalar ratio against spectral index for various models of inflation, and the Planck and Bicep contours shown here. I mean, the thing to take away from this plot is that, first of all, many models with monomial potentials that before Planck were considered, very viable models of inflation, just simple things like phi squared, are now ruled out at high significance. And the range of models that are now favored by the data have these concave potentials. Examples of that include, the earliest model of inflation, just R squared inflation, approximately Higgs inflation, things like alpha attractors and so forth. And many of these models involve inflation just rolling off, the inflaton field rolling off a plateau in the potential, and you're probing a region of the potential where it's very, very flat, and hence producing very small amounts of tensors. So in terms of what this means for future searches for prime order gravitational waves, observers obviously like targets. If you're going to sell your experiment to a funding agency, you need to say there's a natural target that I can look for. That there is a natural target in that there's a class of models that are still allowed by the data, where you naturally explain the value of the spectral index as being of the order of its departure from scale invariance being of the order of 1 over the number of e-folds n star, but that naturally produce tensor modes with an amplitude that goes like 1 over the square of those number of e-folds. And these plateau models, things like R squared inflation, are natural examples of that. So that's a kind of useful thing to bear in mind. As I'll discuss shortly, future experiments, near future, B mode experiments are sort of targeting this 10 to the -3 level for R, where hopefully we might see the signature of these models. Okay, I'm a little bit short of time, but let me just spend 10 or 15 minutes just discussing the future prospects. Much of what I'm going to discuss is based on the microwave background. That's because that's the observable I'm most involved with, but also because, as I said at the start, it's most closest to the primordial fluctuations. So in some sense, it's the easiest to model and is likely to give us the most robust results. So there's a lot of very exciting things happening in this area. Building on the legacy of the South Pole Telescope and the Atacama Cosmology Telescope, there are new ground-based observatories that are coming together and will be seeing first light over the next year or two. One example in Chile is the Simons Observatory. This is sort of building on a collaboration between the Atacama Cosmology Telescope and the Polar Bear experiment. And it's going to build a new 6-meter class large throughput telescope called the Large Aperture Telescope, which is going to survey 40% of the sky to high sensitivity. And then it will include 3 small aperture telescopes. So these are kind of bicep-like telescopes that will be targeting B-mode polarization. And they will conduct a deep survey over a smaller region of the sky. Similarly, at the South Pole, things are moving ahead. And one of the interesting things that's happened recently is that the South Pole Telescope collaboration has started collaborating very closely with the BICEP team. It turns out that to deal with the effect of gravitational lensing when you're searching for B modes, it's very powerful to have a high resolution survey that you can actually use to remove some of these contaminating B modes. So there's a very nice complementarity between these two experiments that has been recognized and is now being exploited. So up until about the next 3 or so years, SPT3G will continue on the South Pole Telescope, and BICEP Array will operate operated by the BICEP team. And then there are plans going forward to develop some of the infrastructure that would point or lead towards a stage 4 CMB experiment. And the sort of infrastructure that they're talking about is a very high throughput 6-meter telescope at the South Pole that would allow many more detectors actually in a larger field of view than the South Pole Telescope does. So you can, in a given integration time, you can get many more detectors on the sky and get much more sensitivity. And also some new infrastructure for these small aperture telescopes as well. Okay, so let's just discuss a little bit about the science that we can expect from some of these measurements. So first of all, I'll discuss sort of non-R inflation science. So this is non-primordial B-mode science. And most of this is going to come from, at least as regards inflation, is going to come from the E-mode polarization on sort of intermediate and small scales. So these data points here, the blue points are forecasts for how well the Simons Observatory will be able to do. And what you see is that it will extend the Planck measurements of the temperature power spectrum all the way to multiples at about 5,000. And similarly, in E-mode polarization, because its noise will be significantly better, about a factor of 5 better than Planck, it can extend its measurements to smaller scales and get exquisite measurements of the B-mode lensing power spectrum as well. So one of the things you can do then with this access to smaller scales is improve significantly measurements of the primordial power spectrum on small scales. So this is just a plot showing if you try to sort of independently measure the power spectrum on a whole range of scales, how well you could do with Simons Observatory compared to, well, Simons is in blue, Planck is in orange in these plots. And of course, on the large scales, you can't really do better than Planck because Planck's cosmic variance limited. But as you move to small scales, there's significant potential for improvement. You know, Planck is these sort of yellowy coloured boxes, and then SO is either the blue or the orange data points. And there's about a 10-fold improvement on these small scales that might tell us something very interesting about the shape of the power spectrum on these smaller scales. And you know, this is getting to scales where we're getting close to those Lyman alpha scales, where we had that sort of interesting difference that I discussed earlier between what the Lyman alpha wants and what CMB wants. For non-Gaussianity, the sort of sad news is that with a microwave background, this sort of inflation-inspired threshold of a sigma FNL of order 1 will remain out of reach. So if you look at forecasts in the local heterolateral and orthogonal models, for Planck, you know, we had measurements with an error bar of 5. With the Simons Observatory, that will improve by a little bit to about 3. Somewhat more significant improvements in the equilateral and orthogonal shapes, but unfortunately still some way away from these sort of theoretical targets that we want to hit. I don't have time to really mention it, but there will be significant improvements in measurements of tensor non-Gaussianity. So inflation can also predict, you know, 3-point correlations between the gravitational wave amplitude and the curvature fluctuations, so correlators of this form. And by making much better B-mode measurements, we'll have much better constraints on the gravitational wave part of this correlator, and hence significant improvements. Okay, where there is very good prospects for improving things by an order of magnitude or so are primordial gravitational waves. So stage 3 experiments like the South Pole Observatory and the Simons Observatory are targeting, you know, they're trying to get down to errors on R of about 0.03. So that's a factor of 10 better than is currently achieved with BICEP. And this is interesting because it starts to get you into reach of these models where R is given by 1 over the number of inflationary folds squared. So the models that are still sort of favoured by Planck data. So this is just an example from the Simons Observatory collaboration showing forecasts in the RNS plane. This is R squared inflation for various number of E-folds of inflation. These are Planck constraints on this model, and these are how well you could do from Simons Observatory. Sorry, is there a question? Yeah.
Yes, sorry. I had a question on this plot. What is the difference between the nominal and enhanced data?
Yeah, so nominal is what is currently funded for Simons Observatory. So that's these 3 small aperture telescopes. SO enhanced is an enhanced version of Simons Observatory, which would have more of these large aperture telescopes, so improve the sensitivity to large scale B modes. So that's not funded. This plot was taken from a white paper that was submitted to the decadal survey, just pointing out the you know, the sort of science reach of an enhanced version of SO.
Okay, great.
Okay. Okay, so what does it take to reach these tiny levels of B-mode signals? So, I mean, the sort of challenges you face are, first of all, the signal is really tiny. The RMS B-mode, if R is 10 to the minus 3, is only 10 nanokelvin. And, you know, compare that to the CMB temperature, 2.7 Kelvin, you can see the sort of dynamic range and the rejection of systematic effects that you would need to make these measurements. We already know from the experience with BICEP and the combination with Planck how important it is to remove galactic foregrounds, and also gravitational lensing is a problem as well. So just to say a little bit about the foreground problem, this is just a power spectrum plot from the Simons Observatory forecast paper. It's quite a busy plot, but the thing I want you to focus on is, first of all, the grey band, which is what the expected foreground power is at the bottom at 93 gigahertz and at the top at 145 gigahertz, where the dust is brighter, in the survey, part of the sky that Simon's Observatory will actually be targeting for primordial B modes. And if you compare that power to the black dash line, which is the tensor power spectrum for an R of 0.01, 0.2, you can see that there's very significant power cleaning that you're going to have to do to remove this emission. The good news is that with a multi-frequency capability of experiments like Simon's Observatory, we think we will be able to clean out these dust modes to a level where we can reveal these primordial signals. The red points here are just an example of this done in a simulation. So the raw power would basically be way up here, and then you use multi-frequency foreground cleaning to get down to here. If you look at the difference of the red points and the black line being the lensing signal, the difference then is hopefully the primordial signal, and that difference is given by this I'm not sure what color to call that. It's kind of a mustardy color line, and the sort of sombering aspect of this plot is that this model, the simulation, actually had R equals 0. So this is actually what you're seeing. These residuals are due to sort of errors in the foreground cleaning. But we know how to improve this. The problem is that you're not properly modeling variations in the dust spectral energy distribution across the sky when you do this cleaning. But methods are being developed that will allow these residuals to be corrected further. Okay, just a little bit about the issue of the lensing B-mode power. So this is just a plot showing what the B-mode power due to gravitational lensing looks like in blue compared to the tensor power, primordial B-mode power, for different values of the tensor to scalar ratio. And what you can see is that as you get down to R of about 10 to the minus 2, the power becomes comparable. So you really have to start worrying and correcting this power. The lensing power actually looks like white noise. It's a constant power spectrum in CL on large scales. So effectively, it acts like having additional instrument noise in your survey, and it actually corresponds to having an additional 5 microkelvin of noise per arc minute pixel. And this is interesting because if your measurements are more precise than that, and with future experiments they will be, with BICEP it will be 3 microkelvin arc minutes. Well, it is now. With future BICEP array, it will be 1 microkelvin arc minute. SA will be a little bit worse. Then this lensing noise is actually more important than the instrument noise, and it's the lensing noise that actually limits how precisely you can make inferences about the primordial gravitational wave signal. Fortunately, we know how to clean this. We can clean this with a method called delensing, and this is something I've worked on a lot recently. I don't have time really to talk about it, but the basic idea is that you take your observed B modes and then you subtract some proxy or some synthetic estimate of what the lensing B modes should look like by combining small scale E mode measurements with some proxy for the effect of lensing in the microwave background. So this could either be lensing estimated from the CMB itself, or it could be some tracer of large scale structure that's highly correlated with CMB lensing. So the procedure for building this template is basically you take these filtered observed E modes on small scales. There's some convolution operation that you take with the proxy for the lensing potential. That gives you these synthetic or template B modes that you then subtract from your observed B modes. And as an example, for Simon's Observatory, we think we can remove around 60% of the lensing power by doing this delensing. And that actually improves the constraints on the tensor to scalar ratio by a factor of 2. BICEP, which has a better noise level than Simon's observatory, is even more limited by lensing. So delensing is even more important for BICEP. And just to say that this improvement in R by delensing has actually recently been demonstrated by the collaboration between the South Pole Telescope and BICEP. And I won't go into the details, but the improvements are very modest, but it's very nice to see a proof of principle of this delensing actually improving constraints on the tensor to scalar ratio. Okay, so just moving even a little bit further forward for the microwave background, after these stage 3 experiments, the next development will be stage 4 experiments, and this is something that's getting very significant traction now within the United States in particular, but with partners both in Japan, in Canada, and across Europe. And the idea is that CMB stage 4 will be an evolution at the moment at the South Pole and what's going on in Chile with the Simons Observatory. And in particular, what stage 4 wants, CMB stage 4 wants to do is a very deep survey from the South Pole targeting primordial B modes. So this will basically involve something like, something roughly equivalent to 6 BICEP array telescopes, with a dedicated delensing survey that will allow very precise delensing, removing about 90% of the lensing power. The hope is that you could reach error bars on R of about 0.0005 as a result. So things like R squared inflation, you could now detect at a good number of sigma. And then it will be complemented by a wider, also deep survey that will be conducted from Chile, where you can access a large swathe of the sky. This will improve very significantly over the sensitivity that the Simons Observatory wide survey will have. And this will be important for all of the other science that you might want to do other than primordial B mode science. On a similar time scale, LightBird should be launched. So LightBird is a JAXA, so Japanese-led mission planning to launch around 2027. And this is degree scale resolution. It's just targeting the large scale signals in the microwave background, but it will have 20 times the sensitivity of Planck. It'll have 15 frequencies, so it can very accurately subtract foreground emission. And it's targeting primordial B modes on large scales. And in particular, these are just some forecasts showing what the power spectrum might look like from LightBird, the E mode spectrum and the B mode spectrum. The black points here are the forecasts. And the interesting thing is that LightBird is able to access the very largest scales because it will conduct a full sky survey. So it can access both the signal on very large scales, which is actually induced by reionization. So this is rescattering of the microwave background at the time the universe reionized, and also the signal from recombination, which gives this bump in the primordial B mode power. So the reason it's nice to be able to make measurements both at reionization and recombination is that you then have some cross-check that what you're seeing sourced at reionization is consistent with what you're seeing sourced at recombination. LightBird is aiming to have the sensitivity to be able to make 5 sigma measurements of primordial B modes on both of these scales if the tensor to scalar ratio exceeds 1%. Okay, just a comment about prospects for actually direct detection of an inflationary background. So this is just a plot produced with, there's some very nice software that Chris Moore and others have put together that allows you to easily put together plots like this. So This is one showing the characteristic strain of gravitational waves as a function of frequency. The black lines here are showing the sort of sensitivity curves of various planned or ongoing experiments. So there's things like advanced LIGO here at these frequencies around 100 Hertz. On lower frequencies, space-based interferometers, LISA here, and proposed things like the Big Bang Observer or DESIGO at frequencies of around 1 Hertz. There are various backgrounds that you have to contend with, astrophysical backgrounds, so binary mergers. But focus on the red line, which is what the inflationary background would be for a tensor to scalar ratio on C and B scales of 0.003, assuming that power law just holds all the way down to direct detection scales. So just to orient you in this plot in cosmological numbers, on the left, the frequencies correspond to 10 to the 5 inverse megaparsecs and 10 to the 15 inverse megaparsecs at these direct detection scales. So, as I said, orders of magnitude away from what you probe with the micro background and other cosmological observables. Even with these very futuristic experiments, this inflationary signal, if R is at this kind of level that you would expect in R squared inflation, will be out of reach, unfortunately. It's also worth...
Sorry, but is it even consistent? I mean, the models have a strong negative V double prime, right? So the energy can't stay the same, it must go down.
Yeah, exactly. Yeah, you're absolutely right. So that's what this slide is actually showing. So something about the dangers of simple power law extrapolation over 18 orders of magnitude or whatever it was. So I mean, this is kind of it's from a recent paper by Bill Kinney, but I think it's a fairly well-known point that what tends to happen actually if you allow more freedom in your inflation model. So what Bill Kinney did here was use this inflationary flow formalism, working with the hierarchy of slow roll parameters to try and consider what might happen in models that are consistent on C and B scales with C and B observations, what the prediction would be on direct detection scales. What you find is that if the power law extrapolation held, then if you specify a value of nt, which is this axis, that will imply the value of R by the inflationary consistency relation, and then you will have some prediction for the tensor power at direct detection scales, which are given by these red points. But in practice, if you allow more freedom in your model in the way you described, then you can get a couple of orders of magnitude less power on direct detection scales, which makes the prospects even worse, of course, for direct detection. So yeah, there's obviously a very big model dependence involved here, unfortunately the prospects don't look great. Okay, I really am running out of time, but if I could just indulge you for 5 more minutes, let me just say about what might be happening with large-scale structure in the future. So we're super fortunate. We've got all these really exciting experiments, either from space, like Euclid and SPHERICS and the Roman Space Telescope, and ground-based things like LSST and DESI, which are all going to be happening in the coming decade and reporting results. So let's just think a little bit about what they might tell us about inflation. And in particular, I want to focus on non-Gaussianity, because I think that's really where the most significant improvements are likely to come from. And in particular, this issue of what does it take to reach this theoretical target of a sigma FNL local, say, of 1. So, you know, being able to distinguish between multi-field models and single field. So the key thing is you need large volumes, right? The CMB constraints are basically exhausted now. What you would hope is that by making three-dimensional measurements, you can have many more modes and hence much better statistics. But to get lots of modes, you need large volumes. And in particular, if you're looking for local model non-Gaussianity, you know, one of the legs in the three-point correlator is large scale. So you want large volumes to access those large scales. And also, if you're looking for scale-dependent halo bias, you also want large scales. Because you are looking for, you know, sort of large-scale phenomena, you only need moderate redshift accuracy, so you don't really need very high-precision spectroscopy. But what you do need to be able to do is control systematic errors very, very precisely. So anything that tends to modulate small-scale power in a large-scale way needs to be controlled very precisely. So examples of this include galactic extinction, the atmosphere, variations in stellar density, and so forth. So this is just a plot from the sort of Spherex science case prepared by Oliver Doré and collaborators, just showing as a function of redshift what the sort of effective volume is that's accessible. The black dashed line is essentially the sort of cosmic variance, so that's the theoretical limit on the volume. Experiments like Spherex get very close to that out to a redshift of about 2. Whereas experiments like Euclid, although will be very powerful, they're some way off reaching this cosmic variance limit. Okay, so what does all that mean for constraints on FNL? Well, this is just a nice illustration of how we can expect errors on FNL to improve going from Planck for the local equilateral and orthogonal model. As we bring in, first of all, CMB stage 4 data, so you know we get some improvements, but unfortunately we don't reach this kind of theoretical threshold that we're after of FNL of about 1. Bringing in large-scale structure data, both scale-dependent halo bias and the bispectrum, and now for local models, things start to look interesting. So Spherex, you know, gets into a region where, you know, the error is about half in FNL local. And then potentially with future intensity mapping experiments like this Puma experiment, which would be a stage 2 21 centimeter experiment mapping about 50% of the sky from redshift 0.3 to 6. You can push that even further. You know, although I think, you know, the prospects from the microwave background aren't great, the interest will move towards large-scale structure probes. So just to finish, let me just note one important technique here that can also improve these constraints on non-Gaussianity significantly. And this is this idea of sample variance cancellation. And this is actually where there's a very nice complementarity between, for example, large-scale structure and the microwave background. So imagine we're trying to measure local model non-Gaussianity. So we're looking for this excess power in scale-dependent halo bias on large scales. If we measure the galaxy density, then that's the matter density at a given wave number times the scale-dependent bias, plus some shot noise contribution due to the fact that we're observing a discrete tracer, in this case galaxies. Whereas if you had some independent direct tracer of the matter density, then you would be observing the matter density plus some reconstruction noise. So, you know, if you were using lensing as a tracer of the matter density, then there would be some statistical reconstruction noise associated with your lensing measurement. And the point is that, you know, if you can get the reconstruction noise low enough and the shot noise low enough, then you can actually measure this bias without any cosmic variance. So crudely, if you imagine just dividing the galaxy over density by the matter density, the tracer matter density, then you know, the actual realization of the modes of the matter density on our sky cancel out, and you get left with the bias, and hence you can measure, or at least significantly eliminate, a lot of cosmic variance from your measurement of local model non-Gaussianity. In practice, you don't do this division, of course. What you do is you combine the 2-point function of the galaxy over density, the 2-point function of the tracer, and their cross-correlation. And the likelihood then will basically take care of taking this difference and cancelling sample variance. So for this to work, you need a highly correlated matter tracer. So you want this thing to be very well correlated with the matter density. And there's a couple of interesting ways the microwave background can help here. One is actually by using radial velocities that are inferred from what's called the kinetic Cenov-Zeldovich effect due to the scattering of the microwave background off moving galaxy clusters. And because you reconstruct velocities in that way, if you then convert them to a density via the continuity equation, you find that there's very little reconstruction noise on large scales. So that's very promising. And also you could use the lensing of the microwave background itself as a tracer of the matter density. And that's also highly correlated with the matter density. So this is just a plot from a recent analysis by Maurice Munchmeyer and collaborators, just showing what might be achievable via this technique of sample variance cancellation on the errors on local model non-Gaussianity. And in this case, they're combining galaxies from LSST with CMB stage 4 kinetic Cenov-Zeldovich measurements of the radial velocities of clusters. So if you just take the LSST galaxies alone and try and look for scale-dependent bias, then you get this orange curve. And this is doing it in sort of different redshift bins. And what you can see is you can't really reach this theoretical threshold of FNL of 1. Whereas if you combine with the kinetic Cenov-Zeldovich effect, you can do this trick of cosmic variance cancellation, and you can start to push down significantly and improve these measurements into the theoretically interesting region. So I think there's a very nice complementarity here between microwave background and large-scale structure measurements, and increasingly in the future, it's the combination of these measurements that will be giving us our most powerful and robust constraints. Okay, so let me just summarize. What I've tried to show in these talks are just that the basic idea that single field slow roll inflation is an excellent fit to all current observations, and I think it's fair to say there's no statistically significant departures, certainly for the CMB data, from this paradigm. The fact that we've measured a spectral tilt, but haven't detected primordial gravitational waves, implies that there's this hierarchy between the slow roll parameters, epsilon 1 much less than the mod of epsilon 2, which rules out most monomial models of inflation. There's a class of models that are still well motivated and fit the data very nicely, which are these models that predict a tensor to scalar ratio R given by 1 over the number of inflationary e-folds squared. So R squared inflation being an example of that. And there's a very clear path forward with the microwave background and B-mode measurements to being able to reach those models. Testing the single field slow roll consistency relation R is -8 NT, unfortunately will be out of reach of next generation space interferometers, both on sensitivity grounds and also because of the model dependence of that measurement. Large scale structure probes promise to take us into this theoretically interesting ballpark where we might be able to see, to discriminate single field and multi-field inflation significantly. And finally, I didn't actually mention it directly in the talk, but reaching constraints on the curvature at this sort of cosmic variance limit of 10 to the -4, which is also very interesting from the viewpoint of models with just enough inflation, unfortunately is kind of out of the reach of stage 4 CMB and large scale structure experiments as well. Okay, well, thank you very much for listening, and I'm happy to take any questions you might have.
Okay, thank you very much for this interesting talk. This was very comprehensive, and we are very happy that you gave this talk. Are there still some questions?
Yeah, I'm still unhappy about H0. I know you didn't want to talk about it, but for me it's like I don't know what the English expression is. In German, there's a Damocles Schwert, something hanging, like a sword hanging over all of it. That you cut the thread and it comes down and destroys everything that you have there, all the beautiful consistency. So what do you think about that? I mean, what is your personal opinion? Can you sleep very well with all this up in the air?
Okay, so first of all, I mean, all of these measurements are very difficult, right? And I think, in terms of potential systematic effects, astrophysical contamination and things, I think it's fair to say that the direct measurements are more challenging than CMB measurements, despite the very small signals involved with the microwave background. So there certainly is, there are people who would argue that you don't have to do very much in terms of systematic contamination in the direct measurements to alleviate this tension significantly. So my own feeling is that I suspect there is some problem with H0, direct H0 measurements, that is not going to explain all of the difference, but some of it. Sort of independent things like Wendy Friedman's tip of the red giant branch measurements are significantly lower than the Hughes measurements of H0. So that's probably part of the story. But I also think it's true that we've probably, with a microwave background, we might just have had a 1 or 2 sigma downward fluctuation in our inference of H0. I think it's likely the combination of those two is actually what's going on. In which case, a lot of what I've said about constraints on inflation will still stand.
Thank you. Okay.
I think what we really need to do though is if someone comes up with a compelling model that does resolve the H0 tension, then of course you can quantitatively check how constraints are going.
But that's the problem. The models are horrible. I mean, I would like to work on that, but I can't bring myself to believe the models that are out there. Okay, thank you. That was what I roughly expected. I just wanted to be sure that you would say that.
It's a bit like sitting on the fence, I'm afraid, but it's.
Thank you. It's okay.
I have a question regarding these very low L anomalies that people have talked about and how they change when you do this more aggressive foreground cleaning to get a bigger fraction of the sky coverage, this analysis you mentioned. Particularly, for example, this alignment between quadrupoles and octopoles that have been pointed out at, I forget, 3 or 4 sigma level or whatever. Did that change anything?
It didn't, because I should have said, sorry, so this analysis by George Stathiou and Steve Granton, where they increased the sky fraction, that was only for the small angular scales that they were doing that. The data they were using on large angular scales was still exactly the same as being used in all previous analyses. Yeah, so there's no change.
Well, it seems that all questions have been answered.